In the last class, we looked at generalized inequalities. Basically, as long as you have a proper cone, you can have these so-called generalized inequalities that can handle that many convex optimization algorithms can handle. Right. So, for example, one generalized inequality is just the basic component-wise inequality. Given two vectors, you say that one vector, say vector x, is greater than or equal to vector y if every component of vector x is greater than or equal to every component of vector y. Now that's a generalized inequality. A more non-trivial example of a generalized inequality is one where you say that if you have two symmetric matrices A and B, you say that A is greater than or equal to B if A minus B is positive semi-definite. Okay. So, and as long as it turns out that this generalized inequality corresponds to the cone of positive semi-definite matrices. All right. So these constraints effectively define a convex cone and therefore a convex set, and therefore constraints that are represented using generalized inequalities correspond to convex constraints. Okay, and towards the end of the class, we looked at one example where you want to perform some kind of a maximization under the constraint that the object that you're looking at is a correlation matrix. And as we know, correlation matrices are positive semi-definite. So that corresponds to basically a semi-definite program. Right? And there are many such examples where it is not immediately obvious that your constraint should correspond to, let's say, a positive semi-definite matrix. But by artificially introducing these constraints, that whatever the variables can be represented in terms of a positive semi-definite matrix, they yield to very surprisingly very efficient solutions. And these have become more popular recently, particularly in computer science. A lot of very hard problems can apparently be approximately solved using semi-definite programs. Right. One particular example is the max cut problem that I had introduced a long time back. If you have given an arbitrary graph, you want to partition the graph into two subsets of vertices for which the number of edges going from one set to the other set is maximized. This is known to be a notoriously hard problem to solve in general. By saying notoriously hard, I mean the computational complexity of solving this problem is very high. But even solving it approximately is hard. And it turns out that for a very long time, people could not do better than just randomly selecting a set, which is kind of a dumb solution. But these semi-definite programming techniques let you do much better than that. And there have been many other problems as well. We won't talk a lot about it, but for example, if you're interested to know more, so please turn off your cell phones. But if you're interested to know more, there's this broad class of algorithms or techniques called sum of squares proofs, which have been of great interest very recently, and they essentially correspond to these semi-definite programming techniques. Okay, so today we look a little more into these generalized inequalities, and perhaps towards the end of the class we'll also look at what are known as dual inequalities. And basically in convex optimization, a sort of fundamental result is this property of, or one fundamental concept is that of a dual optimization problem. So given a convex optimization problem, you can construct another convex optimization problem called the dual problem, and we'll see what is the connection between these two. So towards the end of this course, we'll basically get into duality, and it turns out that the representation in one world can sometimes be more helpful than its dual world, and so on. But more about that later. That's just a sneak peek. But now let's look at these generalized inequalities a little more, right? What is the difference between a generalized inequality and a standard inequality, let's say over the reals? We've already seen some of the properties of generalized inequalities. We've seen that they behave kind of like standard inequalities over the reals, right? So we just recall, yeah. So one property is that they're invariant to addition. So if x is less than or equal to y under some generalized inequality, then x plus z is also less than or equal to y plus z for any z. And it is also transitive. So if x is less than or equal to y and y is less than or equal to z, then x is also less than or equal to z. And it's also preserved under non-negative scaling. So if x is less than or equal to y, then alpha x is also less than or equal to alpha y for any non-negative alpha. It's reflexive, so x is always less than or equal to x. And also, if x is less than or equal to y and y is less than or equal to x, then this implies that x is equal to y. Right? And it's also preserved under limits. And all of these hold only if K is a proper cone. So if some of those properties of being a proper cone are not satisfied, then you don't have all of these properties holding true. One of these potentially might be violated. Right? And that is why we really demanded that the proper cone satisfied all of those properties, that it's pointed, it's closed, it's convex, it has a non-empty interior, and so on. Right? But then there are some properties of standard inequalities that generalized inequalities don't satisfy. For example, if let's take inequalities over the reals. Right? You take any two numbers, let's say 2 and 3. Then either 2 is less than or equal to 3 or 3 is less than or equal to 2. Right? It can't be the case that two elements are not comparable. Given any pair of real numbers, you can always compare these two real numbers. One of them has to be less than or equal to the other. But is that necessarily true for generalized inequalities? Let's say I take two vectors over R2. Right? So one way of defining a generalized inequality, let's take the positive quadrant, that is going to be our proper cone. Then the generalized inequality defined by this proper cone is just the component-wise inequality. So if I take R2, then are every pair of elements comparable based on the component-wise inequality? They are not, right? So this is what is sometimes called a partial order. It means that there are some pairs of elements, so it satisfies some of these properties of inequalities, but potentially it may not have this very important property that every two elements are comparable. So for example, if I take 1, 2 and let's say 3, 4, can you say that these two are comparable? 1, 2 is less than or equal to 3, 4, right? This is clear. But if I take 1, 2 and say 2, 1, now the first component of this vector is less than or equal to the first component of this vector, but the second component of this vector is greater than the second component of the second vector. So these two elements are not comparable. Right? So not all. So let's look at this generalized inequality. So component-wise inequality. Now in R2, suppose I pick an arbitrary point, right? I pick some point. What is the set of all points for which this is the set of all points that are greater than or equal to this particular point for the component based on the component-wise inequality?
We shift the origin to the all points that are in the first quadrant.
Correct. So basically this region is the set of all points. So let me call this point X. This is basically the set of all points X prime such that X prime is greater than or equal to. Okay, so now what is the set of all points for which this point is greater than or equal to okay, or in other words, what is the set of all points less than or equal to X? Complement of this? It's kind of a reflection of this. So this so these are the set of all points which are less than or equal to X under the component-wise inequality. So what exactly is this? Is this set? How do you get it from the cone K? So remember, what was the cone K which defined this generalized inequality?
First one.
It was the first quadrant, right? So can you represent this set based on that particular cone? Yeah, so it's basically a shifted version of the cone. So this is simply equal to the vector X plus the cone K. And what is this set? The set of all points less than or equal to X. It's just X minus K. Does everyone agree? So essentially, if you look at the origin and you look at K, right, the cone K, what is basically K? It's a set of all points which are greater than or equal to 0. Some sense. And what are all the points which are less than or equal to 0? It is minus K. So if you take a particular vector X, the set of all points greater than or equal to X is basically X plus K. The set of all points which are less than or equal to X is basically X minus K. So now if I give an arbitrary set, okay, sometimes it makes sense to talk about a minimum. So if I give a set of real numbers, let's say it's a closed set, then this always has a well-defined minimum. But obviously we saw that not every pair of elements are comparable. But sometimes, even though not all points are comparable, some sets can still have a well-defined minimum. Right? So let's try to visually see some examples to see when you might have a minimum and when you might not. So suppose I have, let's say, a closed set which looks like this. Do you think this point has a minimum? And if so, what would be the minimum?
We're still considering a component based.
Yes, we're still looking at component-wise inequality. So let me call this set A. Does A have a minimum? And how do I define a minimum? So we say that some x, let's say x star, is equal to the minimum of A if, well, of course, x star is less than or equal to x for all elements in A, and x star should also be a point in A. Right? So not every pair of points within A could be comparable with each other, right? But you can compare x star with every single element in A, and x star is less than or equal to every single element in A. Right? If something like that exists, then I call that the minimum. Okay, so in this particular example, this set that I have drawn over here, do you think this set has a minimum?
Yes.
Does everyone agree that this set has a minimum? Okay, and if so, what is the minimum? Yeah? Yeah, so this the vertex on the bottom left. This point would be the minimum. This is my x star. And how do we argue that this is indeed the minimum?
X star plus.
Yeah, so you look at x star plus k. So what would x star plus k look like? This entire region. So when would x star be a minimum point? Exactly, when basically x star plus a contains the x star plus k contains the entire set A. Right? But not every set could have a minimum. Right? So let's look at this particular set. Yeah. Can you think of an example where the set does not have a minimum? Which does not have a minimum according to the component-wise inequality. Let's focus on R2. Yeah?
Diamond.
Okay, a diamond-shaped set. Or so any set which looks like this. right? So now you can't really find a point which is less than or equal to every point in A. Now this set does not have a minimum, or if you want something perhaps more concrete, something which can be represented in analytical form, you can take the following set, take the following half space x1, x2 such that x2 is greater than or equal to 0. What does this set look like? So what is x1 plus x2 equal to 0? Yeah, it's a line with passing through the origin with what slope? It's -1. So it's a straight line. This is x1 plus x2 equal to 0. And what is x1 plus x2 greater than or equal to 0? Which half space is it? Is it above the line or below the line? Above the line. So it's basically this set. And this set does not have a minimum. But what this set does have is essentially a set of what are called minimal points. So we say that some x is basically a minimal point of A if you cannot find any other point in A which is less than or equal to x, other than x. Okay, so what is a minimum point? A minimum point is basically a point which is less than or equal to every element in the set. Okay, what is a minimal point? A minimal point, so we say that some point is a minimal point if you cannot find any other points from that set which are less than or equal to this. Think. Okay, so let's take this particular example. Okay, this set. Okay, that's what we've drawn. The set of all x1, x2 for which x1 plus x2 greater than or equal to 0. Does this have a minimum? No, everyone agrees that this set does not have a minimum, right? But is some point on this minimal? Let's take the origin. Can you find any point in the set which is less than or equal to 0, 0? How many say yes? How many say no? Okay, if yes, can you find a point which is less than or equal to 0, 0 within this set? Yes. So let me take any point in the interior of this set. Okay, let's pick this point over here. Is there a point in A which is less than or equal to this particular point? Yes, there is. Can you give me a point? The origin is less than or equal to this point that I have marked in yellow. Okay. I take any point on the interior, I can always find some point along this line, x1 plus x2 equal to 0, which is less than or equal to any point I mark on the interior. But if I take a point on the line, can I find a point which is less than or equal to that point on the line? In particular, let me take the origin itself. Can I find any point in this set which is less than or equal to 0, 0? You can't, right? And why is that? Yeah? Yes. So if I look at, okay, what's the set of all points which are less than or equal to 0, 0? It is basically 0 minus k, correct, which is this set. Now this set is fully contained in the complement, or in other words, there's no intersection with the set A at all. So there are no points in the set A which are less than or equal to this particular point. So this is an example of a minimal element. It's not the minimum, but it is a minimal element, and there can be multiple minimal elements for a given set. In this particular case, what is the set of all minimal points? All points along the line are basically minimal points, right? Yes.
Minimal points should lie in the set.
They should lie in the set. Yes. Okay. Maybe it's not here, but yeah. So minimal point. If.
No, we said no. Y is less than A. Y belongs to A. So y is equal to.
Yeah. So that automatically implies. Y less than or equal to x and y is in A implies y is equal to x. Well, it need not. If A is, if this is not satisfied at all, then you could still call it minimal, but let me say that x in A is a minimal point if this is true. Okay. Similarly, just like a minimal point, you can also define a maximal point. So a point is maximal if y is greater than or equal to x and y is in A implies y equal to x. Right? Any questions? Okay. So recall that when we were talking about convex sets, I mentioned that there are two different ways to view a convex set. One is that you could view a convex set as a convex hull of a closed convex set can be represented as a convex hull of some particular set. And it can also be viewed as an intersection of half spaces. Correct? We'll make this a little more formal now. So a very useful property of convex sets, one that has applications in many different areas, is this notion of separating hyperplanes. So given any two sets, suppose I have two sets A and B. Now you look at a particular hyperplane, let's say A transpose X is equal to B. So we say that this is a separating hyperplane, or this hyperplane separates So we say that this hyperplane is a separating hyperplane for A comma B, or this hyperplane separates A and B if one set lies exactly on one side of the hyperplane and the other set lies on the other side. Right? And we'll say that this hyperplane strictly separates A and B if these inequalities hold with strict inequality. Okay, so visually speaking, if you can draw these two sets, then it means that you can draw a straight line which strictly separates these two sets. All right, so you draw this set, you have another set, then this hyperplane basically separates these two sets. That's just the visual interpretation. An important property of convex sets is that if you have two sets, A and B are convex, that don't intersect, then there is a separating hyperplane. But this doesn't necessarily hold true for non-convex. Can you think of a non-convex set for which you cannot construct two non-convex sets which have zero intersection, which have empty intersection, but it's impossible to construct a hyperplane which separates these two?
take a circle and cut a
Okay, yeah. So take a circle and cut a slice.
slice.
Okay, sector. Right. So you call this set A, and let's say that this set is B. Then it's impossible to construct a hyperplane which separates A and B. Right? Any other examples?
You have a regular shape.
Okay. So like this. Yeah.
One more which can get in that but not touching. Yeah, some.
Something like this. Right? This also doesn't have a separating hyperplane. And so in particular, suppose I mean, this is a useful property to have in many cases. For example, if you are constructing classifiers, right? A simple linear classifier is one which basically distinguishes between half spaces. You try to construct a hyperplane which separates the two. So suppose you wanted to classify between elements coming from A and elements coming from B. That's a basic binary classification problem. Then a linear classifier is basically a hyperplane which separates these two sets. So in the language of convex sets and convex functions, a linear classifier is just a hyperplane which separates two sets. All right, and if your sets are non-convex, then it may or may not be possible to construct a linear classifier. Right? I will not prove this particular statement. There's a conditional proof in the Boyd and Vandenberg textbook, but the most generalized proof requires, it's not terribly hard, but it requires many other results that need to be developed in order to come to this particular stage. So we'll assume that this is a fact and this is true, and just go on with it. All right. But what this is helpful with is the following property, right? But before that, the statement says that if you have two convex sets which don't intersect, then there exists a hyperplane that separates A and B, right? Then there exists a separating hyperplane. But the converse is not necessarily true, right? Just because there's a hyperplane which separates A and B does not mean that the two sets, and you know that A and B are convex, it doesn't necessarily mean that that the intersection is empty. Think about it for a minute. Again, we're talking about separating hyperplanes. So just stare at this for a moment and try to think about why the converse is not true. If you have, can you construct two convex sets, A and B, for which the intersection is non-empty, right? Two sets A and B, convex, intersection is non-empty, there's a separating hyperplane, but the intersection is not empty. There are elements common to both sets. Yeah. Can be any two intersecting sets on the hyperplane. In particular, if the two sets intersect along the hyperplane, then that hyperplane is still a separating hyperplane. Right? For example, let's take the most simple example of two half spaces. Right? The set of all x such that some A transpose x is greater than or equal to B, and this is my A, and my B is the set of all x such that A transpose X is less than or equal to B. Are these two sets convex? Are these two sets convex? I don't hear a loud enough response. Okay. Is there a separating hyperplane? What is a separating hyperplane? So A transpose X equal to B is a hyperplane which separates A and B. What is the intersection of these two? A transpose X equal to B. So the intersection is non-empty. The two sets are convex, but they're still a separating hyperplane, right? So the converse is not true, but then if you add some additional constraints, for example, if there's a strictly separating hyperplane, or if you say that one of the sets has to be open, right? So remember that convex sets need not be closed. You can also have open convex. So if you demand that one of the sets is open, then the converse holds. So under certain conditions, the statement is true. The converse is also true, right? So just like you have separating hyperplanes, for a given set, you can also define what is called a supporting hyperplane. And the supporting hyperplane kind of generalizes the notion of the tangent to a particular curve or the tangent for a particular set. So you take any point, let's call it x naught, which lies in the boundary of a particular set. Right? So recall that the boundary is basically the closure of A minus the interior. Okay. So you take any point in the boundary and you say that a point, so the following, a hyperplane of the following form, A transpose X is greater than or equal to A transpose X0. So this is a hyperplane which passes through X0. So we say that this is a supporting hyperplane for the set A. if all of A lies exactly on one side of the hyperplane. Sorry, the hyperplane should be this equal to A transpose x0. So in other words, A transpose x is greater than or equal to A transpose x0 for all x in the set. I claim that every point on the boundary of a convex set has a supporting hyperplane. So, but before we prove this, let's take a non-convex set and see if there always exists a supporting hyperplane at every point. So let's take a point that looks like this. If I pick a point over here, so basically what is a supporting hyperplane? It's, if you look at this particular curve, the boundary is a curve in R2. Basically it's a tangent. If you can draw a tangent such that all of the set lies on one side of the tangent, then that's a supporting hyperplane for that particular set. Potentially there could be multiple supporting hyperplanes at some points. But the question is, does every point on the boundary have a supporting hyperplane? For this particular set, does every point have a supporting hyperplane? Okay, can you give me one point which does not have a supporting hyperplane? It is not convex, yes. So can you give me a point where you don't have a supporting hyperplane for this set? So basically, take any point over here, right? So for example, if I take this particular point, then the tangent to this particular point will be something like this. And the set A lies on both sides of this hyperplane. So for these points, there is no supporting hyperplane. But for all the points, let's say on this side, there's a supporting hyperplane. But the claim is that if the set is convex, then every point on the boundary, there is a supporting hyperplane. Yeah.
Can there be a non-convex set
Yes.
where every point on the boundary has support?
Every point, if it is closed and it okay, I'll come to that. Suppose that the set has a non-empty interior and the set is closed, then there cannot be a convex set which has a non-convex set having a supporting hyperplane at every point. So remember, all of this makes sense, or it's non-trivial only if the set has a non-empty interior, right? Because you can have a set which is fully contained in a hyperplane. If you look at any set of dimension less than n minus 1, then there's a hyperplane which contains that entire set, right? So then it could be convex, it could be non-convex, doesn't matter. But if it has a non-empty interior, then the converse is also true. If there's a supporting hyperplane at every point on the boundary, then the set is convex. Okay, but before that, suppose now let's take the separating hyperplane theorem for granted. Can we use that to prove this particular claim? Remember this, the separating hyperplane theorem says that given any two convex sets for which the intersection is empty, there exists a hyperplane which separates these two. What I want to show is that just using this alone, I want to show that every point on the boundary has a supporting hyperplane.
We take any x naught
Okay.
and we take some kind of reflection of the set above x.
What do you mean the reflection of the set?
Something with it x naught plus k, x naught minus k.
Okay.
X, I'm not sure what kind of.
What is K?
That's what I'm not sure. But like some
Okay.
kind of reflection about the point, then there are two convex sets. So
Okay.
there has to be a
Okay.
which cannot intersect.
Yeah, so then how do you find this K? That's the question. There's something simpler. So firstly, if the set has a smaller affine dimension than n minus 1, then the statement is clear because there's a hyperplane which fully contains the set, and that's true. So it's the only part you have to show is when it has a non-empty interior, right? So in other words, in R3 it's a solid set. It's not a plane set in R3, for example, or something which is contained in a line in R2. So let's take a convex set, right? Convex. Take a convex set. Take any point on the boundary and try to construct a supporting hyperplane. So in this case, the supporting hyperplane passes through the face, right? Our goal is to somehow show that this supporting hyperplane is also, if you want to invoke the separating hyperplane theorem, then this should be a separating hyperplane for something, right? So let's pick x naught to be one set, just the set containing only x naught. This is going to be one set. Basically what I'm trying to do is I am given a set, let me call this C, that's my convex set. I want to construct a supporting hyperplane. I want to show that there is a supporting hyperplane at any point on the boundary x naught. So I want to somehow split into two parts. I want to split C into two parts and then construct a separating hyperplane. So I have x naught, which is A. This is a convex set because it contains only one element. Now from the remainder of C, can I construct another convex set? So first, is C minus x naught a convex set? It's not, right? Or at least it need not be. Okay, what other convex set can I construct? Suppose I look at the interior of C. Is this a convex set? It's a convex set, right? And what is A intersection B? Yeah. It's a null set, right? Because B is basically C minus every point on the boundary. Right? You're removing all of the boundary and basically you get B. Right? So the intersection is empty. Is empty, and whatever, A and B are convex. So there exists a separating hyperplane. So basically there exists some vector such that A transpose X is greater than or equal to B for all X in the interior. And A transpose X is less than or equal to B for all X in A. But can A transpose X not be strictly less than B? So think of it this way. I started with a convex set, right? And I defined two sets. One is this point x0, which was in the boundary. And I defined another set, which is basically everything in the inside of this particular set. So you remove only the boundary and you get an open set. And that was my set B. Now, the separating hyperplane theorem guarantees that it's possible to construct some hyperplane such that B is fully on one side of that particular hyperplane. So in other words, I can draw a line such that B lies fully on one side of that particular line, and the point x0 lies on the other side of that particular line. But where on the other side of the line can this point x0 lie? It has to lie on the line, right? Is it possible that it does not lie on the line? No, right? Because after all, B is the interior of the set, right? So this x0 is arbitrarily close to B. Correct. So x0 is on the line. Basically, it is on the separating hyperplane. So what does this imply? Yeah,
The separating hyperplanes also support.
it's also a supporting hyperplane, right? So A transpose X is greater than or equal to B for all X in the set C.
We were writing like a fully formal proof.
Uh-huh.
Is that a completely rigorous statement in this, or like how do we prove that?
Which one? This?
The X naught is on separating.
X naught is on the separating hyperplane. Yeah, it's not fully rigorous in that sense, but effectively the argument would be that how far can X naught be from the separating hyperplane? Can the distance be strictly greater than 0? No, obviously, because the minimum distance to the interior is basically 0, and that's how we would argue. But yeah, I'm not giving a fully rigorous proof, but it contains all the essentials.
You can also prove this using the definition of a convex set.
Which one?
The same supporting line.
How?
Basically, you're checking whether every point on the boundary is a tangent.
Correct.
So you take any point in the convex set,
Okay.
then take a convex combination with the boundary.
Okay.
Inside the
So
inside the set. Yeah.
sure. Again, also another point to keep in mind is that the hyperplane itself is an n-1 dimensional object. It doesn't have dimensions smaller than this, and that it's subtle in that sense. All right. So what this says is that for every point on the boundary, you can construct basically a tangent or a supporting hyperplane such that the entire set lies on one side of the tangent or the supporting hyperplane. So what would be the intersection of all the supporting hyperplanes taken across the entire boundary? The set itself, right? So in fact, what would be the intersection of all the half spaces defined by all the supporting hyperplanes? So, okay, let's take an example. Consider the circle. All right, so what is a supporting hyperplane? It's basically a tangent to the circle. Now, for every one of these tangents, the set, in this case, the circle, lies on one side of this tangent, right? Now, for each point on the boundary, I have a tangent and a corresponding half space. What would the intersection of all of these half spaces put together be?
Boundary of the
Intersection of the half spaces, the set itself. The intersection of all the tangents themselves would give you the boundary. Well, not the intersection, because not even the union, right? But the intersection of all of these half spaces put together gives you the set itself, right? Of course, all of this is assuming that you have a closed convex set. So every closed convex set So one way of looking at the convex set is as the intersection of half spaces. Sorry?
Wouldn't it just be the interior? Like, why would the boundary be so?
That's because of the way I've defined the half space, right? The half space is closed, right? So it's the set of all x for which A transpose x is greater than or equal to B. So that will end up being a closed set, and that gives the closed convex set itself. Right? But instead, if I looked at the set of all x for which A transpose x is strictly greater than B, then that would give me the interior of the convex set C. All right. Now, suppose I have a polyhedron. Right? Take any polyhedron you want. How many half spaces do you need to generate this polyhedron? 4, or in general, finitely many. Right? What are the supporting hyperplanes at various points on the boundary? So if you take any face of this, what would be the supporting hyperplane? Yeah, it's basically the straight line which contains this particular edge. Right? But what about a point on the vertex? There are infinitely many supporting hyperplanes, but there's also another important property that you take any other point on this boundary, right? Take a point on the edge, but which is not a vertex. You construct a supporting hyperplane. How many supporting hyperplanes do you have? Exactly one, right? At least in 2D. Right? And what is the intersection with the set itself? How many points are there? Infinitely many, or definitely more than one. But suppose now that I take a vertex, right? Then what is the intersection of the tangent with the set itself? 1. Of course, it's possible to construct a hyperplane for which that you have infinite intersection, but there's also a supporting hyperplane at the vertex which contains exactly one point from A, and that is the vertex itself. Right? So such a point is what is called an extreme point. Now let's think about a polyhedron in R3. Right? Now on the boundary there are 3 kinds of points. One, points which correspond to vertices. Right? So let's take a cube. So you have these vertices, you have the edges, and you have points on the face which are neither vertices nor edges. Which of these points would be extreme points if we looked at this as a definition? Vertices are obviously extreme points because it's possible to, so what is a supporting hyperplane? It's a tangential plane, correct? So at any point on the vertex, it's possible to construct a tangential hyperplane for which the set is completely on one side, the cube is completely on one side, right? And this plane contains only the vertex. It doesn't contain any other point in the set. What about a point on the edge? Is a point on the edge an extreme point of this particular cube? It's not, right? Is any point on the face an extreme point of the cube? It's not, right? Okay, so basically these vertices are the only extreme points of a polyhedron. Right? Now what if I have a curved surface instead? For example, in R2, I just take a circle, or whatever, the region enclosed by the circle. Which are the set of extreme points? Every point on the boundary is basically an extreme point, right? The nice property of extreme points is that you can generate any point in the interior, or basically any point in the set, purely by a convex combination of extreme points.
Can we say that extreme points always lie on boundary?
Yeah, so by definition, an extreme point is always on the boundary, but not every point on the boundary is an extreme point. So this gives a different view of the convex set itself. So on the one hand, you can think of the convex set as obtained by taking the intersection of half spaces. But on the other hand, you can also view this as the convex hull of all the extreme points. Now, sometimes you may need whatever infinitely many extreme points to define the set. For example, in the case of the circle, all the points on the boundary correspond to extreme points. But in the case of an object like a polyhedron, you only have finitely many extreme points, basically just the vertices, right? And many of these have algorithmic implications. So in many cases, particularly in linear programming, the complexity of the algorithm that you use either depend on the number of half spaces that are used to describe the polyhedron, or the number of extreme points, depending on which algorithms you choose to use. Right? Again, I'm not going to prove this particular property. It's a very nice result. But these are two different ways of looking at or generating a convex set. All right. Okay, so maybe we can stop here. Any questions? Questions? Okay, so let's stop here.